Okay, the second talk in this session is by Xiaodong from University of Washington, and he'll be talking about observation of fractional quantum anomalous Hall effect.
Do we have a microphone?
Oh, sorry. I still have the microphone.
You can give a talk.
All right.
Okay, thank you. Okay, I would like to thank the organizer for the invitation and to this Ultra Quantum Matter workshop. And today I'm going to tell you something I'm really excited about is this fractional quantum anomalous Hall effect. I'm going to call it FQHE. Just to define, right, this fractional quantum anomalous Hall effect is fractional quantum Hall, as everybody knows, but a zero-magnetic field and without the lambda level formations. So we know that the quantum Hall effect probably is right, the landmark discoveries in the condensed matter physics. And these just early data, from these pioneering papers. What they measure is Hall resistance, RH, as function of the magnetic field, and you will see a lot of plateaus at the particular magnetic field, or the filling factors. And what's really remarkable is that these Hall conductance is in a particular form, right? C times E squared of H, and the C is the chain number. Now we know that. The reason it's remarkable because we know the material itself, right? It's actually quite dirty systems. But these kind of collective behavior of electrons and show you that the resistance is quantized. Therefore, now we know that this remarkable phenomena is coming from the topology of the systems. As my colleague, David Paulus, and his collaborator, right back to 80s, they showed that these systems and the chain number can be defined by the integral of battery curvature in the unit cell momentum space. And later, I think a couple of years later, and Chen-Niu, Solis, and also Wu, they come up with another paper. I think quite exciting is that they show basically extended the previous TK-KM paper into the regime with many about interactions and also with substrate disorders. So in this paper, they basically able to show that the fractional chain number also is a topological invariant. And in this particular paper, I think the time when they did this calculation, there's no dependence on magnetic field, although I don't think they also realize fractional quantum anomalous Hall effect, but they don't consider magnetic field in this particular paper. So now the question is how can we realize this kind of quantum Hall effect at zero magnetic field? And Duncan Hoden, right, he came up with this toy model back to 1988 and shows that the integral quantum Hall effect actually can be realized in this honeycomb ladder structure, and Monica talked about lots of these effects we call quantum anomalous Hall effect. But the zero magnetic field version of a quantum Hall effect actually be theoretically established much later, at 2011. So there's quite a few papers discuss how you can realize these fractional quantum Hall effects at the zero magnetic field, or you call fraction translators. So key ingredients for this effect is you need a topological band, you need a strong electron-electron interactions, and also you need a spontaneous time reversal symmetry breakings, right? Because we're talking about zero magnetic field. And one key element to realize all these ingredients is that we need a flat chain band. And only theory paper is they basically propose, you can realize such a state, but doesn't point into a particular material systems. So there's a lot of theory work being proposed, like all kinds of material systems. Relevant to my talk is this Mori superlattice. And Monica already gave a pretty good introduction on the materials. I think the motivation is coming from, right, Pablo's his landmark experiment shows that in this twisted graphene, you can engineer these unconventional phenomena, right, more than just superconductivities, I think. So people got motivated, and there's a theory work, from Harvard, from MIT, right, also shows that this effect is a fractional quantum anomalous Hall effect actually can be engineered in this Mori superlattice. In all these theory work, they point into these graphene Mori superlattice because that's the system when it was hot. Indeed, there's quite a few exciting progress. So shows that the fraction changes later, but in the presence of a magnetic field. So the first work is from Andre Young's group. They studied the Maurice soup lattice formed by bilateral graphene and HBN. They found these fraction chain insulator states in the presence of above 30 Tesla of magnetic field. And then the collaboration between Pablo and also Amir, they also show that in match angle twisted bilateral graphene, these FCI states actually can exist at the low magnetic field. Roughly they show up started about 5 Teslas. So both experiments actually establish thermodynamic evidence of these FCI states, but in the presence of magnetic field. Then we go back to the same question, right? How can we realize this FQHE state, which is, I think it's an anomalous Hall effect, but with a fractionally quantized Hall conductance at the zero magnetic field. So what I'm going to tell you today is that we can realize these FQHE state in the twisted MOT2 bilayers. And my talk has 2 parts. The first part I'm going to show you are optical measurements of the 3 quantum anomalous Hall state with chain number -1, -2/3, and -3/5. Use these magnetic circular diaphragm measurements and also use optically detected fine diagrams. And then in the second part, I'm going to show you the transport measurements. So we pretty much show the same states, but except we see another new state at -1/2. I'm going to tell you why we can see in the transport, but not in the optics. Okay, so just briefly, the material system we use belong to the transition metal dicogenide. The famous one is MOS2, right, discovered by Tony Hans and Feng Wang back to 2010. So in these monolith TMDs, if you look at these crystal structure from top, they form this honeycomb lattice structure and with cocktail and a metal right, on each of the corners, so they break these inversion symmetry. An important consequence of this inversion symmetry breaking is that give rise to this valley-dependent barrier curvature and also orbital magnetic moment proposed by my collaborator Di Xiao and Wang Yao and Idil. So this effect actually, this valley-dependent property form the foundations for this topology physics I'm going to tell you. So imagine, right, we take one layer of this TMD and stack on top itself. Then we form a bilayer, but with a little twist. So this is called rhombohedral stacking soup lattice. So in this type of AA stacking structure, there's 2 energy degenerate minimums in Mori lattice. We call B and C. So B is with metal on top of cocktail, and the C is cocktail on top of metal. Then these 2 sublattices, they form a honeycomb lattice structures. Back to 2019, right? These 2 papers already showed that in these TMD homobilayers, you can study topology physics. So yeah, the first one is from Allen's, and the second is from my collaborator Wang Yao. Both papers actually study the twisted MOT2 system. So our work actually just started from there because my collaborator Wang, he told me you should work on these materials. Even though at the time he doesn't know there's a fraction quantum Hall state, fraction quantum normal states in this particular system, but he knows it's topological, at least based on the theory. And let me just briefly go through the theory, one slide, and give you kind of an idea why the system is topological. So if we look at these electrons' equation of motions, right, we have the 2 terms. So the first term is about the positions, right? You can see that there's a omega k term, and in the second part is omega r. So omega k is the barrier curvature in the momentum space, right? Equivalent to a magnetic field in the momentum space. And the second part is actually it's the barrier curvature effect, but in the real space. So usually for the single crystal we deal with, it's a homogeneous crystal. Therefore, this term of this omega r, which is barrier curvature in the real space, it's ignored. We don't have it, right? Because the crystal is homogeneous. But then the situation changes in these Maurice sublattice. So let me just walk you through it, right? I told you we have 2 Maurice sublattice, B and C, which are energy degenerate. B is with metal on top of cocktail. C is cocktail on top of metal. Then you can imagine if I start to evolve from, move the position from B to C, then this local atomic registry must change, right? Then these forms these Maury atomic textures. You basically can consider these as a layer pseudo-spin textures. And in Allen's paper, basically shows that these are layer pseudo-spin skirmers. So we know if there's a skirmer in a real space, then you have this real space vector curvature and give rise to this emergent magnetic field. So this is the original topology of these homobilayer systems. We started working on this material back to 2019, but I'll have to tell you, initially it doesn't work. So my students all got discouraged. Then there's another two papers come out. One is from Liang Fu's group. They studied the twisted WSE2, and it shows that there's a quantum anomalous Hall effect at twist angle of about 1.4 degrees, and also with indication of this FQHE state. And the other one is more relevant, is from the collaboration between Kai Sun and Shi Zhenglin, ETL. What they show is that in MOT2 systems, actually, they did this many body calculation. They found this chain number. Basically, you can have this fraction chain insular state near the twist angle of 1.4 degree as well, just consistent with Liang's calculations. Then my student got really motivated because now I have two more papers, right, showing that indeed there's something exciting and with twist angle 1.4 degrees. So we started working on these systems for about a year, and it turns out, we're just like this little puppy. Actually, 1.4 is not a right angle. Then my student got discouraged again. Then I told him, okay, well, forget about this 1.4. Let's just try something, right? So this we're going to tell you today. And the initial twist angle, what we found actually what's working is random, right? It's around like 3.5 to 4 degrees. But now, we test a lot more devices, and the others also in the community test a lot of devices. I think the range we can safely say have these QH, and the FQH states is between 2.6 to 4 degrees. But this range, I think, it's a dynamic range. I think with more and more device made, probably the range will also be expanded. But the take-home message is that actually it's not as very sensitive to a twist angle if the twist angle is large, okay? But it's not 1.4. It's just a joke. It's not an offensive joke, okay? So anyway, I'm going to tell you is that we discovered these correlated ferromagnetic insulating states at both integer and the fraction Maury fillings. Use these magnetic circular dichroism, right? We need a spontaneous time reversal image breaking. And the second part is then I'm going to show you how we can use optical technique to determine these quantum anomalous Hall state. The details can be found by these two papers. So I know a lot of theorists sitting in the audience, and I want to scare you with this diagram is how we measure this dichroism. There's a lot of components. The only reason is here is try to scare you. The important part is the bottom part. I'm not sure if you can even see it. Is we basically sending a laser beams and modulate it between right circular and the left circular polarizations. Then we send these polarization modular light to a sample. We measure the reflection difference between left and right circular polarization. So we call MCD, which is a magnetic circular dichroism. So MCD measurements, if you're not familiar with it, you can think of it as a measurement of a Hall conductivity, but at the optical frequencies. Okay? So that's all I'm going to tell you. Then we're going to use this MCD technique. Here, just one example, what the signal look like. And this is what we measured many years ago on this monolayer ferromagnet in collaboration with Pablo's group. And what I show you is that the MCD signal as function of a magnetic field sweeping up and sweeping down. So there's a key features, right? You see there's a finite MCD signal at the zero magnetic field, and then also you see a hysteresis loop. So all these are hallmark of a ferromagnetism in a monolayer. Then we perform the same measurement on these. The data I show you is from 3.9 degree twisted MOT2 bilayers. And here's a schematic of samples. We have a dual gated structure, means we can control doping in the sample. We can also control the perpendicular electric field across the samples. So in this diagram, the vertical axis is the filling number, means the number of carriers per Maury unit cells, and the horizontal axis is electric field. And you can see that in this large free space, right, only at the whole doping site we have this non-vanishing MCD signal with which suggests we have a ferromagnetic state, at least phase space. And there's also two features here corresponding to the fraction filling and also integer fillings. Just to confirm, we do have these ferromagnetic states. I pick a spot in the phase space at the integer fillings. Then we can perform these MCD measurements as function magnetic field. You can see these hysteresis loop, right? As I already told you, which is a hallmark of ferromagnetisms. We can also measure these MCDs as function temperatures, and you can see the hysteresis vanishes as we raise the temperature. So the Curie temperature of the system is about 14 kelvins. It looks like not too high, right? It's a low temperature, but actually, if you think about it, it's really high temperature because my Mori unit cell has a wavelength about 5 nanometer, and the feeding factor is 1, means there's 1 carrier every 6 of 5 nanometer of unit cells. Then the carrier density is really low, right? The spin density is very low, but and it's also in the 2-dimensional. So the Curie temperature actually 14 Kelvin. So this already indicates something unusual in the systems. Then the next question is, okay, then how can we measure the chain numbers, right? Initially, we cannot do transport. So there's 2 ways to measure chain number. One is just do transport, if you can. If you cannot, then you just measure the Venn diagram and use the Strata formula to fit this dispersion curve. So look for these thermodynamic evidence of the states. So here are just 2 examples, right? You look at the density of the gap states and as function magnetic field. So this was from Amir's paper. They look for these chain number from these fractional chains like states. And the other example is from Aliastani. They do STM, right, which you cannot do transport. They also look for this dispersion curve to determine all the chains later in magic angle twisted graphings. So we can use the same trick. But the probe we use is we call trions. So just give you, a brief introduction what is trion. If we shine light to a semiconductor, right, you create an electron hole pair. They bond together. They form an exciton. So this is neutral. But if we dope the system, say I dope with holes, then these exciton going to bond to extra hole. They're going to form a 3-particle system. So this is called trion. Here's a typical spectra, photoluminescence spectra from a monolayer MOT2. And you see we have a neutral exciton emission, and we have charged exciton emission. You can see there's energy separation between these two. So you can clearly tell, right, there's a trion formations. If I continually tune my carrier densities in this vertical axis, what I show you here is luminescence intensity plot from a monolayer. You can see a neutral exciton at the charge neutral. Then you see trion appears. The intensity is sort of continuously tuned. Okay. Now, what I show you here is actually a trion intensity plot as function doping, or I already convert to feeding factors, but for a twisted valley MOT2. Then in this plot, you will see that there's 2 kinks in terms of feeding factor. Right? The first kink points to these minus 2/3 feeding factor. The second pointing to -1. So these 2 kinks, right? You see the trion luminescence actually drops. The intensity drops. So the reason is that, as I mentioned to you at the beginning, right? Trion is exciton bound to a free carriers. Okay, but in a system when there's a correlated state forms, means there's a gap state form, then the subfermi surface is gapped. The number of free carriers to form trion actually is reduced. So you can think of the number of trion also going to be reduced. Therefore, the luminescence from the trion will also be reduced. So what we do is that we're basically looking for the reduction of the trion luminescent population. This is a signature of the formation of a gapped state. Okay? Then we can compare this luminescence intensity plot to my MCD measurements. You can clearly see, right? Whenever there's a gap state, right, we see there's a sort of enhancement we have this little bump for these MC signal. So from these kind of comparison, we can establish we have a ferromagnetic insulating states. So the next step is then we do the same measurements, but at the different magnetic field, right? So from 0 Tesla all the way to 4 Teslas. And if you look at the carrier density, for example, correspond to this -1 filling, you will see that, right, actually it changes as from your magnetic field. Basically, there's dispersions. So this tells us there's something actually topological. But this is very not quantitative, right? To do some kind of a quantitative comparison, what we do is that we perform a spectral integrations of these luminescence, right, over these spectral windows. Then we plot these spectrally integrated PO as function of filling factor at the particular magnetic field, for example. Then you will see there's two dips correspond to these two gapped states. Okay. Then I plot these line traces as function magnetic field and get these Venn diagrams. And in this Venn diagram, you will see there's three features here, 1, 2, 3. All right. Then we can compare these three features with the dispersion compared to these strata formula analysis. So these are the three expected lines from these topological states. And the first one, where you can see all these lines actually can fit to my data really well. Okay. So from this comparison, what I conclude is that the state at the filling factor -1 is a quantum anomalous Hall state, and the other two at the -2/3 and also -3/5 correspond to the fraction quantum anomalous Hall state. So these are the measurements we have. At the same time, my colleagues, my collaborator, Di Xiao, and also Liang Fu, they did independent calculations on this system to see if whether measurement makes sense. Because initially, right, 1.4 degree doesn't make sense. So they want to see what's going wrong. So both of them come up with similar conclusions. Here, what I will show you is the result from Di Xiao. And what we learned is that why it's wrong, because, well, what they found is lattice relaxation actually plays a really important role to shaping the Moiré minibands. That's how you determine the trace angle. So what he found is that for the optimal trace angle for this FQHE effect actually is between 3 to 4 degrees. So we basically got lucky, make such a sample at the right angle. Then he also did a calculation to find these many-body chain numbers, 2/3 and 3/5. He found these the gap from 2/3 actually is slightly larger than the 3/5. So there's a lot of TMD system, right, proposed. I think a lot of people ask me what's unique about the MOT2. So one possibility is, well, the band is really flat. So what it means is the bandwidth actually is smaller than 2 millieV. Just to give you a comparison, for magic angle graphene, the bandwidth is on the order of 10 millieV. Okay, so it's already flat band, right? But this is much flatter. The second is there's a very strong electron-electron interactions give us these ferromagnetic states. And the third one is there's ideal quantum geometry. You can see what it means from Ashburn and his collaborators' paper. All right, so let me see how much time I have. Okay, not much time left, sorry. Does spin orbital coupling play role? I would say yes. Yeah, because this gives rise the spin valley locking effects in the TMDs. And so part one already take a lot of time, but I'm going to go to this part two, where the part one is give you a thermodynamic evidence. So the part two is where I show you the transport measurements. Here just one of the main results. Right, we perform these measurements of these longitudinal resistance Rxx and also Hall resistance Rxy as function of electric field and the carrier densities in these plots. And there's a lot of things going on in these plots, right? You see, for example, the filling factor -1, -2/3. You see there's kind of a reduction, right, compression of Rxx. But at the same time, you will see enhancement of Rxy. So this already tells you, well, there's something interesting going on. So let's do a little bit of careful study. So I took these Rxy measurements and plotted as function magnetic field. Basically, it's a Venn diagram measurement. And you can clearly see there's three dispersion features. And then we can fit it to this strata formula, get the chain number -1, -2/3, -3/5. And also when you flip the sign of the magnetic field and the slope, right? The sign of the slope also flips. This basically tells you, right, it's coming. It's not a quantum Hall state. Actually, it's a quantum anomalous Hall state. So the take-home message of this kind of data is consistent with our optical measurements. Actually, right? Basically, it's the same measurements, just use different probes. Next is then we're gonna do these magnetic field measurements. So the first is at the at the filling factor -1. You will see the Rxy is quantized at the edge of the square with a nearly vanishing Rxx at the zero magnetic field. This is precisely the hallmark of quantum anomalous Hall effect. And we measured it in 3 different devices with different trace angle, 3.5, 3.7, 3.9. They basically show very similar behaviors. So the results, I think, is really robust. Yeah, the nice thing about the system is that you can apply electric field to control these quantum anomalous Hall state. One feature I want to show you here first is the temperature dependence, right? Well, I emphasize that even at the 8 Kelvin, Rxy is still nearly quantized. You may not appreciate this number, so let me show you this paper from Yoshi Takura. So we know that the QH is initially discovered 2013. So this year is marked like 10-year anniversary. This is kind of a review article published about a month ago about this quantum anomalous Hall effect. So what you see that the end, where I say today the challenge is to push these QH effect to higher temperatures. First to 4K, then to room temperature. And I think we probably already achieved this goal at least the first goal. Yeah. Then we can show how we can use electric field to tune this state. I think I don't have time. I will just skip these. But the take-home message is that we can use electric field to tune this state from this quantum anomalous Hall to this insuling state, which is ferromagnetic and consistent with a couple of theory predictions. I'm going to skip all these, actually, because for the interest of time. This next part I want to show you. What do I mean here is that we measure the thermal activation gap of this quantum anomalous Hall insulator as a function of the electric field. So we see that this thermal activation gap is about 30 kelvins. As we tune this electric field, actually the gap eventually shrinks and vanishes, then increase again when it transitions to a ferromagnetic insulator with topological trivial. So this shows you how we can use the electric field to tune the phase transition from one gapped phase, which is topological, to another phase, which is topological trivial. And consistent with all the theory prediction you can think of, right? The gap must close. Okay, so now I'm going to shift gear to these fractional quantum anomalous Hall state. First, I want to show you the line cuts of these Rxx and Rxy as function filling factors. And we see a few humps, right, corresponding to this fractional filling 2/3, 3/5, and this basically is a signature, right, of this fractional quantum anomalous Hall state. Another interesting feature is that you see the Rxy actually linearly increase as carrier densities and across almost 2 edge of the square at the filling factor -1/2. So this shows that at the -1/2, the state probably compressible is distinct from this 2/3 or 3/5 state. All right, so first thing is we can do the same measurements, perform Rxy measurements as function of magnetic field and also Rxx. You will see this Rxy is pretty much quantized to the 3/2 with nearly vanishing Rxx. So the quantization is about 1%. Okay. And we can also do the same measurement for the 3/5 states, and the quantization is about 3%. And we can also use electric field to control the phase transition from this fractional quantum anomalous Hall state to a topological trivial state. What I show you here is electric field, and the blue curve is Rxy, where you see Rxy will quickly drops and vanishes. And we see the Rxx initially was nearly vanishing. The increase seems like to a insulating state, then drops again, seems like to another metallic state. So we don't know exactly the nature of this state. There's something still under study. I still want to emphasize, right, this feature is high temperature. So what I show you here is the data from this 2/3 state as function of temperature. From the top to the bottom, I increase temperature from 0.1 Kelvin to 3 Kelvin. So what I highlight here is even at the 2 Kelvin, the state is still nearly quantized. Right? So this shows basically tells you the energy gap is pretty large. And we can perform these thermal activation measurements again, and they give us this gap of the 2/3 states is around 20 Kelvin, and the gap for these 3/5 states is about 14 Kelvin. But I have to warn you that the thermal activation gap measurements is not very accurate, right? Yeah, Leon is shaking his head. But I will tell you, you can trust this number very much, right? But those thermal activation gap is not very accurate. But the take-home message is it's a large energy gap. Yeah. All right. So last, I want to touch upon these 1/2 state. We can do the same measurements, right? RxY as function magnetic field, and it looks like a quantized, but don't be fooled by this plot. This doesn't tell you the state is quantized. Just tell you there's anomalous Hall signals, and with the anomalous Hall with RxY is 2h squared. But if you look at these RxY as function filling factor, right, you see it's almost the linearly increase. Means the state is compressible. Okay, so it's not any fractional quantized state or any quantization. So what's going on? Well, I don't know, but I'm an experimentalist, right? I'm kind of superficially compared to what already been done in the past for a 2D electron gas system. So this beautiful data, much more cleaner than what I show you, is that if you focus on these you focus on this 1/2 filling as function magnetic field, right? You will see this RxY is about 2h squares. Now, if I compare these two data, if I look at these data from 2D electron gas first, right? As I tune the magnetic field equivalent to the filling factor, you see the first bump, 2/3 state, second bump, 3/5 state, some little bumps, then linearly increased. Okay, this really looks similar to what I have here, right? One bump, second bump, then linearly increase. So there could be some kind of intrinsic connections between these two phenomena. And when we have the data, and I'm very happy to see two actually preprints on the archive. Well, I didn't tell Ashton or Liang my data at all. They don't know my data, and I don't know their theory as well until it's come out in the archive. So what they say is that these minus 1/2 quantum anomalous Hall state is actually a zero field composite Fermi liquid in this MOT2. Okay, so we have some signature, right, for that. And recently we did some other more measurements and also support these interpretations. Okay, so finally I will show you, the phase diagram I showed at the beginning was kind of a small part of these whole measurements. But you can see that what I show you is Rx, right, as function of large field, as function of filling factor. There's a lot going on in this plot. And there's very rich phase diagrams. For example, right, at this 1/3 state, what we see is a CW state. It's not a topological. And many of you may wonder, right, 1/3 seems very robust. Why not a FQHE state? Why is it a CW? Honest answer is I don't know. But you can ask Liang Fu. He has these calculations. But the calculation is done after the experiment, so you have to be careful what it means, right? So what they show is when the theta is away from the optimized trace angle, this is the phase diagram he predict. Right, you have 1/3 is CWs, 1/2 is composite Fermi liquid, then you have a 2 fraction quantum anomalous Hall state. If at the optimal trace angle, there's a lot more states going to show up. So that's what we are looking for right now. And there's also interesting predictions from CENTO, right? How you can tune this electric field and from this composite Fermi liquid to a Fermi liquid state. But what we can see here, now this is 1/2 state, right? When I tune my electric field, you will see this Rx actually will dramatically increase, then drops again at a very high electric field. So this sort of a suggesting we have a transition from some metallic state to an insuline state and to some kind of metallic state again. So this might fit into CENTO's this picture, which is he suggests there might be a weak disorder in the system. So in the intermediate electric field regime, there could be P in the CW state. All right. The take-home message is there's a lot of interesting things. Last one, I think actually very important, is this phenomenon. I believe, right, this twisted MOT2 system is highly robust because there's already a couple of groups obtained very similar results. So the first one is from Cornell group. They did these external sensing measurements. They observed this fan diagram, very similar to our optical measurements, then observed these 2/3 fraction quantum anomalous Hall state. And the other is a transport measurement, and found a group in China, they also observed these 2/3 fractional quantum anomalous Hall state. But the 3/5 state has not been reproduced yet. I think, from my own experience, is that this state actually is very fragile and has very high sensitivity to the quality of the samples. One example, right? If you look at these quantum anomalous Hall state from these transport measurements, you see its quantization is up to 1.5 Kelvin. It's not 8 Kelvin, as I just talked to you, right? And this minus 2/3 FQHE state actually is not fully developed even at the 600 millikelvin. So it's also not a 2 Kelvin I just told you. So I think this probably has something to do with the sample qualities. Right? But the overall take-home message is that I think the system itself is very robust and could be good news for the experimentalist. Okay, so here's my conclusions. I will leave it here, but I would like to thank my students. These 3 students, they did the most work. And thank all the theorists and my colleagues for help in the transport, and also the crystal from the Japanese group. And thank you for your attention.
Okay, thanks for another great talk. We can take some questions.
Yeah. Is there a reason you saw these fractions only on the hole side and not on the electron side?
Yeah, so first, because it's light assistant, so there's no electron-hole symmetry, right? Because it's a light assistant. Very different from quantum Hall. The second is... I
thought you have like direct points and then
it's a semiconductor. Yeah. And the second is why hole bands. The honest answer is I don't know. But I can tell you what I think what's happening is that there's a very strong spin-orbit coupling induced splitting in the whole band. It's about 200 millieV. Okay? But for the conduction band, the spin-orbit coupling is very weak. It's about 30 millieV or even less. So that might be the reason. Yeah.
If you go back to the slide where you're comparing it to the gallium arsenide plateaus, why does the RXY come down? I mean, that's not a feature you see
Excellent question. Yeah. So why it's come down? This actually says the system has something new. So I'm gonna repeat what Liang he told me. Okay. So what he thinks, there's a phase transition from the 2/3 state to the rest, filling factors. So if we believe the -1/2 is a composite liquid state, a zero magnetic field, then this composite liquid state actually is a parent state for many states around these filling factors. Okay, so what it shows is if we take what I told you is correct. What it says is that the 2/3 state doesn't share the same parent state of these 3/5 state. Yeah, that's what it means. I think Ashwin is here, right? Maybe he can tell you more. He was here. He just left. Yeah. Oh, you're here. Yeah. I thought you tried to avoid a question. Anyway, so that's what I learned. Yeah.
He's allowed to avoid the question. We had another question back there. Maybe you can just say it.
This is very exciting. I noticed that in your MCD,
Yeah.
in the range from 2/3 to 1, there's a lot of MCD signal. It seems from the transform measurement, RXY is almost zero.
Yes, excellent questions.
Can you repeat the question?
So this is very good questions. Let me just look at this. So the question is that in my MCD measurements, right, magnetic circuit diaprism, from the whole phase space, there's ferromagnetic states, okay? But in my transport, you look at in this plot, right? Looks like RXY is very small in this regime. So that's the question, right? The question is why MCD shows strong signal, but RXY is small. So if we compare these two plots, right, one is RXX, the other is RXY, you will see that in this particular regime, we call anomalous Hall metal regime, okay? So RXX first is very small, and RXY also very small. But the ratio between RXY to RXX is actually not small. So the Hall angle is about 30 degrees. Okay? So this phase, we tentatively assign it to anomalous Hall metal regime. Yeah.
I guess another feature in the MCD is that when you get past -1, filling and you go like further, you have this feature that seems to kind of like disperse and go to finite
Yeah.
displacement. Do you know what that is?
Yeah. Well, know, I didn't. Let's see if I have. So we basically explained in our first paper, about these ferromagnetic states. Okay, so what's going on there is that first of all, it's also an anomalous Hall metal regime because you dope it, right? So you dope it into the metallic regimes, and basically it's these. So these guys actually, it's a ferromagnetic metal phase. That's a simple answer. Yeah.
But why finite displacement?
Oh yeah. The reason is that when you apply electric field, you basically redistribute the electrons between these two layers. Okay, and so what the calculation shows that is at a certain displacement field, the electron wave function from top and bottom layer is overlap the most somehow, and then we need these electron wave function overlap to have this direct Coulomb exchange to give rise to these ferromagnetic states. But then if you go electric field goes even larger, imagine if you go larger, you push all the electron into one layer. Okay? In that case, then the ferromagnetism will just vanish because the system becomes layer polarized. Yeah.
Maybe I can comment on your question.
Yeah.
So one difference between the gallium arsenide and your platform, you have a dispersion in your bands. It's not large, but you have a dispersion.
Yeah.
So you are allowed to get a Fermi liquid, which you cannot, a regular Fermi liquid you couldn't get in the lambda level.
Yeah.
And that's competing with your fractional states.
Mm-hmm.
So, presumably between -1 and -2/3, like as you also suspect, the fractional states lose the competition and you get the metal instead.
Yeah. So basically, there's a phase transit into something, right? Then come back to the topological. Yeah. Thank you for help.
Any more questions? No. Okay, one more. There we go.
How do you interpret the Arrhenius plots? Or why are they interesting?
Can you repeat the question?
The question, I can repeat it. How do you interpret the Arrhenius plots, and what was it? And why are they interesting?
Well, how do you interpret
The plots for the gap, where you extract the gap, the Arrhenius plots.
Yeah. How do we extract it?
Why is there
What is the significance of the log plots of the resistivity?
Yeah, so the plot itself is a measurement of a thermal activation gap of the systems. And it sort of tell you, not a very accurate way to tell you what's the energy gap of my state. Because it's important, right? If a large energy gap means you can study the system in high temperatures. Yeah. So that's what the plot is. But like I told you in my talk, is that plot itself, you take it, but don't trust it too much. The much more reliable results is when we measure these RxY Sony magnetic field at the different temperatures. Right? We see condensation is still there around 2 kelvins. So that one is very solid.
Oh, now we have more questions suddenly. Mike.
So there was some indication that it was the CFL, some experimental indication?
Yeah. I'm going to tell you October 2nd. Precisely.
October 2nd. What time?
Mike hasn't told me the seminar times. I don't know.
Max, yeah.
So this factor of is following up.
Yeah.
This factor of 10 mismatch between the Arrhenius slope and the.
Yeah. Yeah. Yeah.
Can you repeat the question?
So I think the question is in my RxY measurements, right? It's almost quantized the 2 Kelvin. But in the Arrhenius plot, for example, the thermal activation gap is about 20 Kelvin. So you're saying why there's 10 times difference, right? So a simple way to understand this is imagine I have a semiconductor, and you're excited with excitons, right? Exciton is excitation. A semiconductor gap is a single particle gap. So, but there's a difference between this optical gap to the single particle gap, right? So that's the same thing here. So basically, what we have here, 20 Kelvin is a measurement of the gap at the particular low temperature. You see what I'm saying? The 2 Kelvin is, you can think of it as a Magnum gap. right? It's limited by the magnetizations. But if you measure something at, for example, 100 millikelvin or 2 Kelvin itself, the thermal activation gap is a single particle gap.
You think maybe it's the first order transition or something?
No. So what I'm saying is a simple way to think about it is if you're a semiconductor, that's what I'm trying to bring out. Let's just repeat myself. You create an exciton, right? You know that there's optical gap. So the optical gap is always smaller than your single particle gap. So the temperature-dependent measurements RxY, right, is limited by, eventually, if you raise up temperature, imagine when the magnetization vanishes, right, you cannot measure RxY anymore. Make sense? So that's the gap determined by the magnons. That's the excitation gap. Okay, you can think of it like excitons, right? When your magnon is, you flip one spin to the other side, it's like excitons. Okay? But this thermal diffusion gap is like a single particle gap measurement.
I think the charge gap is much.
Basically, yeah. Yeah, that's right. Charge gap is much bigger than the magnon gap. Yeah, exactly.
I think it's a fairly subtle question, but it's one that arises often in quantum Hall systems. It's not uncommon that the activation gap is considerably larger than the temperature at which the quantization goes away. So I'm not sure one should make too much of it. But, all right, one last question.
So you have these sharp transitions, right? Like this function of displacement field. It would be interesting to study how those that transition point changes with temperature. That'll give you an indication, relative entropy, for example, of the two phases. Did you look at that? How the phase boundary, how these phase boundaries change with temperature?
We look at it in terms of MCD. We did these type of measurements at different temperatures, but not in the transport. We haven't done very careful measurements function, the whole map.
Okay.
Yeah. We did the particular feeling, but not the map. So that's a very good suggestion, actually.
All right. I'm sure there are plenty more questions that'll be asked during the break. I'd just like to thank the speaker for a healthy mix of both appreciation and skepticism for theory.
Yeah.